In this lesson, we're just going to talk briefly about the intermediate value theorem and the multiplicity of zeros. So the intermediate value theorem says that if we let f be a polynomial with real coefficients, if f of a and f of b have opposite signs, then there is at least one value of c between a and b for which f of c equals 0, or equivalently, the equation f of x equals 0 has at least one real root or real 0 between a and b. So I know that's a lot of words to kind of walk through what each of that means. So that if we have some sort of polynomial f, if f of a and f of b have opposite signs, remember the function value means your y coordinates. So if we have some a for x, we have an f of a that might be negative, so below our x-axis, and then we would have some other value b, which again, different signs means that it would be a positive. What that means then is that there's at least one value of c between a and b such that f of c equals 0. Well, f of c equals 0 means that y equals 0. Y only equals 0 when we cross the x-axis. So if I have some point a, f of a down here, and then I have some point b, f of b up here, well, in order for it to be a polynomial function, it's continuous, so there's no breaks. That way the function would have to go from f of a up through f of b. Well, what happens then, what has to happen is that if there are different signs, which is part of the conditions that we have here, is that our c would have to be where the graph crosses our x-axis, which means that there is some value c that is a real root or a real 0 between a and b. The fact that it crosses the x-axis means that there is a real root or a real 0. So let's do an example to see how the intermediate value theorem can be used. If we're given a function g of x equals x to the third plus 4x squared plus 4x, we want to use the intermediate value theorem to determine if the function has a real 0 between -4 and 1. So going back to our intermediate value theorem, in order for there to be a real 0, that means that when we find the function value of -4, so f of -4, and the function value for 1, f of 1, we should get opposite signs, right? Those y coordinates or the function values should be opposite signs. If we do, then the intermediate value theorem says that there is a real 0 between -4 and 1. So with that, that means that we're going to need to find g of -4 and g of 1. So for g of -4, again, we're just substituting in. So we have -4 to the third plus 4 times -4 squared plus 4 times -4. Lots of 4's. So -4 to the third is going to be -64. Doing our order of operations on our next term, we have -4 squared would be a positive 16. A positive 16 times 4 is going to be a positive 64. And then on our last term, 4 times -4 is going to be -16. Well, -64 and 64 will cancel out, so we'll just have -16. So g of -4 gives us -16. Next, we want to find g of 1. So that's going to be 1 to the third plus 4 times 1 squared plus 4 times 1. So that way this is going to be 1. 1 to the third is 1 plus 1 squared is 1, and then 4 times 1 would be 4. Right, you do square it first, then times by 4. Plus 4 times 1 is 4. So 1 plus 4 would be 9. So we found these function values. So using our intermediate value theorem, we need to determine if there is a real 0. Well, again, the intermediate value theorem says that if the function values are different signs, then there must be a real 0. Well, since we got the function value of g of -4 was -16, g of 1 was 9, the fact that these two answers have different signs means that there must be at least one real 0 between -4 and 1. There might be more, but there is at least one real 0 between -4 and 1. So next we want to find what the zeros of the function are, all of them. Remember, zeros, sometimes they'll be called roots, sometimes they'll be called x-intercepts. Those words are all interchangeable. So when it says to find the 0, that means to find the root, which also means to find the x-intercept. So again, finding our x-intercept means that we're setting the function equal to 0. So we're going to have x to the third plus 4x squared plus 4x equals 0. So if possible, we always want to try to factor first. So here I have a greatest common factor of x. So that way we're left with x squared plus 4x plus 4. Again, then I can factor the inside. X squared plus 4x plus 4 would factor into x plus 2x plus 2. Or more generally, we can say that x times x plus 2 squared, since we have two identical factors. Which means that when we're solving, we have our factors of x and x plus 2. So I would set each part equal to 0, so I'd have x equal to 0, x plus 2 equals 0. Well, x equal to 0 is already solved for x. X plus 2 equals 0, we can just subtract the 2 on both sides. That way we have x equals negative 2. So your zeros of the function would be at x equal to 0 and x equal to negative 2. Again, also note that with the x plus 2 squared, I did just take out what was inside the parentheses, because with the square, if you can still walk through all those steps, but essentially what happens with the square would cancel out when we're solving using our square root property. We have the square root of 0, which is just 0, so we can shorthand that to just take the inside to do x plus 2 equals 0. So now that we have the zeros, we want to find the exact multiplicity of each zero. So your multiplicity is essentially the number of times the zero appears when we're solving for it algebraically, as we just did. So this can happen in one of two ways depending on how you solve the problem. The first would be to either look at the exponents of the individual factors. So coming back up to what we just did, is that looking at our factored form, which would be the x times x plus 2 squared, the x would be your first factor, and then the x plus 2 squared would be your second factor. So looking at the exponents of the individual factors, the x has an exponent of 1, and then the x plus 2 squared has an exponent of 2. So that would help us to determine the multiplicity. Another way to do it would be the number of times your zero appears in your answer. So how this might be helpful to you is if you didn't rewrite it how I did, it's x plus 2 squared. If you actually stopped at this point and said, okay, I'm going to solve this, you would get x equal to 0, x plus 2 equals 0, and x plus 2 equals 0. And in solving that, you would get one answer of x equals 0, you would get another answer of x equals negative 2, and then another answer of x equals negative 2. Well, the fact that you got the same answer, x equals negative 2, twice, means that we would have that x equals negative 2 has a multiplicity of 2, because you got negative 2 as an answer twice, which again, going back to the first way that you could look at it, would be when we had that exponent of 2, that shows that our multiplicity would also be 2. So for x equals 0, we would say that it has a multiplicity of 1, because either going back to our exponent saying that we had an x to the first, that x to the first gave us an answer of x, one answer of x equals 0. So x equals 0 has a multiplicity of 1. X equals negative 2, going back to its factored form, x equals negative 2 came from the factor of x plus 2, but x plus 2 had an exponent of 2. So x equals negative 2 has a multiplicity of 2. Or, if you didn't rewrite it as x plus 2 squared, solving them individually, you get x equals negative 2 and x equals negative 2. Again, it appears twice, so its exact multiplicity for x equals negative 2 would be a multiplicity of 2, since it appears twice. That's finding the exact multiplicity, saying how many times it appears. Knowing the multiplicity of each zero helps us then to determine what happens to the graph of the zero. If the zero has an even multiplicity, the graph would touch the x-axis and turn around at that zero. So if the number that we found for the multiplicity was even, then the graph would touch the x-axis and turn around. If the zero that we found had an odd multiplicity, the graph would cross the x-axis. So, looking at what we had before, we had x equals 0. So x equals 0, we said had a multiplicity of 1. 1 is an odd number. We don't care about the actual 0, we care about the multiplicity. So since the x equals 0 had a multiplicity of 1, 1 is an odd number, that means at x equals 0, the graph will cross the x-axis. So go from either positive to negative or negative to positive. At x equals -2, we had a multiplicity of 2. So 2, that multiplicity is even, which means that the graph touches the x-axis and turns around at x equals -2. Looking back at what we did with the intermediate value theorem, hopefully this should make a little bit of sense because we said that there should be at least one real zero. We actually found between -4 and 1, we actually found 2 real zeros, but the fact that the graph changes either from positive to negative or negative to positive shows that there was at least one real zero between -4 and 1. And we actually found 2 real zeros. We found x equal to 0 and x equals -2. So again, knowing the multiplicity and how it relates to the graph will help you when you're graphing the full polynomial function.